Good afternoon. I'm Adam Sales, currently of UT Austin College of Education, but very soon of Worcester Polytechnic Institute. This is joint work with my longtime colleague, John Pane. I'm going to talk about an observational study within the Cognitive Tutor, which is now called Mathia, but it was called Cognitive Tutor when we did the study. I'd like to think that the study doesn't only pertain to Mathia, though. I think it also has something to say about teacher autonomy, about mastery learning, about observational studies in EDM. But hopefully I can convince you all of all that. Here goes. So the way Mathia works, Cognitive Tutor at the time, is that it shows students math problems, and in our case, Algebra 1 problems. And each one pertains to a certain set of Algebra 1 skills. And every time a student works a problem, Cognitive Tutor, or Mathia, estimates the probability they've mastered all of the skills, and then uses those probabilities to choose the next problem. And if they've mastered all of the skills in a section, they get promoted to the next section. And that's the structure of mastery learning, that the students master skills and move on through the curriculum as they master the skills. It doesn't always work like that. One possibility is wheel spinning. The students will work and not master skills, and they get promoted anyway. Another possibility is that the teacher goes in and changes the student's placement within the tutor, overrides the mastery learning structure in order to show different material to different students. And that's what we're going to focus on now. We want to know whether that affects student post-test scores. Is reassignment a good thing? I don't know. There are actually different ways you can think about it. In one sense, teachers can see things about students that the software doesn't have access to. The teacher can know sooner whether a student is wasting their time with the section, whether it's working, whether it isn't, and can move students around that way. On the other hand, when teachers move students around, it undermines mastery learning. It changes the order of the curriculum. Maybe that's not a good thing. We don't know. I just heard a talk from Neil Heffernan that was saying that actually students all moving together at the same pace is better than each student moving on their own. And reassignment is something that would help teachers do that. So it's unclear whether that's actually how they use it. So we're going to use data from the RAND Cognitive Tutor Algebra 1 Effectiveness Study, which was a huge randomized trial to estimate whether the Cognitive Tutor works at all. So they compared schools where the Algebra 1 classrooms used this software, used the tutor, and had their own special curriculum, versus schools where they didn't. They just did business, whatever they were doing previously, business as usual. And then they measured, they measured learning with a 32-item multiple choice post-test. And they found that in the first year there wasn't much of an effect. In the second year, there was a substantial effect that was statistically significant in high school. I say substantial because in education field trials, a fifth of a standard deviation is substantial. We're going to use data from that study, but not the whole study, because the study wanted to know what the effect of the tutor was. We want to know what the effect of reassignment within the tutor is. So that means we're only using data from the treatment group who used the tutor. And we're also not going to use data from people we don't have log data for. So we had to throw that out. We also only focusing on high school because we think high school works differently than middle school in terms of Algebra 1. But we're still going to keep that post-test score because that's how we're going to measure learning. And that's actually very useful for this study. We don't have to look at the next problem correctness. We can use a third outside post-test score. When you do that, actually, we can look at the difference between pre and post-test. It kind of looks like reassignment's good. The more students are reassigned, the higher their post-test score. Though this is a really raw comparison. And the other thing is, after this slide, we're only going to look at whether students were ever reassigned versus never. So it's going to be a binary variable. Reassigned versus not reassigned students. If we really want to estimate the effect of reassignment, we need to compare similar students. And it turns out that reassigned and not reassigned students are not actually similar on average. Special ed, ESL students are more likely to be reassigned. People with missing free or reduced place lunch status are less likely to be reassigned. White students much less likely. Latino students much more likely. There are a lot of differences between who gets reassigned and who doesn't. Not to mention what classroom they're in, which also probably has a pretty important difference. So we gotta adjust for all this stuff. So how are we gonna do that? In an ideal world, we would find basically identical matches of students who are as far on all of our observed covariates exactly the same. And then we would compare their post-test scores. One reassigned and one not, and if the reassigned students did better than the identical not reassigned students, then we would say reassignment looks like it helps. We can't actually do that. Instead, we're doing something called propensity score matching, which is supposed to be almost as good, actually, where we estimate the probability that a student would be reassigned given their covariates, given their pretest scores, classroom, etc., etc. And those are called propensity scores. And for every student, we estimate a propensity score, this probability of being reassigned. And then we find groups of students, some reassigned, some not, that have very similar propensity scores. Sometimes it's a pair of students, sometimes it's a group of students. But then within those groups, which are supposed to represent basically identical students, students that have the same probability of being reassigned, then within those groups, we can compare post-test scores. We can compare the post-test scores for reassigned versus not reassigned students. This is all under the hope that matching on propensity scores, which is what this is called, gives you similar looking groups, which it's supposed to do, but it doesn't always. You have to check that, which we're going to do. Now, either of these approaches makes this huge assumption that we measured all of the important covariates. Anything that might predict reassignment and simultaneously predict post-test scores was measured. All confounding is measured. Of course, that's the big advantage of randomized trials, is that you don't have to make this assumption. We do, and we're going to make that assumption for the next several slides, but then we're going to try to relax it a little bit. We're at least going to try to account for the possibility that we missed some important confounders in our uncertainty estimates. But hold that off. For the moment, let's just assume that we measured all the important confounders. So we have to now estimate these probabilities. We have a multi-level model to do that accounts for what classroom they're in and what school they're in and what state they're in and who their teacher was, and actually also lets the effect of pretest score vary within classroom, because maybe there are some classrooms where the advanced students are reassigned, other classrooms where the less advanced students are reassigned. We want to account for all that in the model, and we do. That's the magic of multi-level models. Then when we actually find similar students, we didn't actually just use the propensity scores, like I said a couple slides ago, that you just match people on propensity scores. We also matched them on pretest scores, because we wanted pretest. We wanted matched students to have very, very similar pretest scores on average. So we added that in as extra emphasis. And we also threw out students who couldn't be matched. If there were not reassigned students who we couldn't find any reassigned students who were similar enough to them, or vice versa, we threw them out of the study. And so all of the estimates for the rest of the talk are going to pertain to the blue dots. What is the effect for these blue dots? And I'm not going to bother trying to extrapolate that effect to some bigger population. That seems like a hard problem. It's hard enough to try to estimate the effect for the blue dots. And then we can think about a larger population after that. Right, so after we composed these matches, threw out some students, matched some other students, on average, matched students look really similar. The green dots is these same z-scores, except within matches now, averaged within matches. And they're really close to zero. That means very little difference between between the groups. In fact, there was better balance on this set of covariates than there would be in 97% of matched randomized trials. And there was also very good balance on classroom. Students tended to be from the same classroom. Not always, but they tended to be. So we're adjusting for that as well. Now, if we were just to estimate it without doing all that, just comparing reassigned to not reassigned students, we'd get an average effect of, negative 0.05. But once we use the matched comparisons, matched reassigned students did about a fifth of a standard deviation worse on their post-test than their matched comparisons, than the not reassigned students. That's basically just as big as the effect of the tutor in general. You can do some extra regression for some other covariates. Doesn't really change much. You can, compare year 1 to year 2. Looks like maybe it's a lower effect in year 1 and less of a negative effect in year 2, but can't really say for sure. Confidence intervals overlap, etc., etc. So those are our estimates. That's our estimate for the average effective reassignment for the students in the study. But this all assumes, of course, that we measured all the important confounders, which we didn't, I'm pretty sure. I don't know what we missed, but I'm sure we missed something. So we want to incorporate that into our uncertainty, because when you don't measure something, it just means you're more uncertain about it. The way we're going to do that is by imagining an unmeasured confounder that predicts both reassignment at a level that we specify as TZ and predicts post-test scores at a level we'll specify as rho squared. And we, instead of pulling these numbers out of thin air, we estimate what they would be for pretest, had pretest not been included. If we hadn't had a measure for pretest, what would its TZ and rho squared be? And since pretest is almost always like a super important covariate, we figured this is a pretty conservative way of thinking about unmeasured confounding. And if there were an unmeasured confounder as important as pretest in terms of TZ and rho squared, then that increases our uncertainty like this. We're more uncertain about effects, but not uncertain enough that we think they might be positive. In fact, we're still pretty sure they're negative. Leaving out a confounder as important as pretest can't explain the direction of the effect. It can mean it might be smaller than we think or bigger than we think, but we're still pretty sure it's negative. Another thing is that all these effects are on average across all students. That's not true. I mean, it's not the same effect for everybody. So how do we get around this? Well, we looked to see if there were different effects in different classrooms with a multi-level model that regularizes the classroom-specific estimates. We found this, a pretty wide variety. In some classrooms, there might have even been a positive effect. In other classrooms, a negative effect. But take this with a little extra grain of salt. We don't know how unobserved confounding works with heterogeneity, especially since it might work differently in different classrooms. So let's take it with an extra grain of salt. With that said, let's think a little bit about what might predict the effects within classroom. These are just totally hypothetical and exploratory. But one thing we thought about was the variance of pretest scores. If maybe the way students, some teachers use reassignment to account for varying abilities and varying paces. Didn't really find, we couldn't say for sure one way or the other with this one. With the proportion of students who were ever reassigned, there's a little bit of evidence that there might be something there. That in classrooms where fewer students were reassigned, maybe that means teachers are using it in a more targeted fashion. There's less of a negative effect, maybe even a positive effect. When everybody is reassigned, or a lot of people, then the effect is negative. So here's our conclusions. We can be fairly confident that on average, reassigning students lowers their post-test score. On average, as long as we, there aren't too many, too important unmeasured confounders. But it also looks like in some cases reassignment not only doesn't hurt, but helps, possibly. We don't actually know where, for sure. I also hope I convinced you that observational studies have a role in EDM. That you can, if you're careful enough and you think about unobserved confounding, you can get something valuable out of observational data. Have a great afternoon. Thank you so much. Now I'll take questions.